like C++ and Java and some other things, is how it handles object-oriented programming. So it uses traits instead of like classical inheritance. And this is, a lot of people don't really like this. You can mimic a lot of the same things you can in C++, but there are, you kind of have to take a different approach. So like if I want to have structs for circle, square, and rectangle, and I want to be able to print the area for all of them, then I create a trait called shape with a function prototype, and then I implement it for all the structs that I want to apply to, which looks a little bit different than it would if this were C++, in which case like square would inherit from rectangle or something like that. But traits are unable to access the like member variables of a struct that they operate on, which is a little bit strange, or it's new to people who are accustomed to C++. It means if you like it really just boils down to if you go into Rust with a C++ mindset, then like you can't use inheritance normally, and you have a little extra code duplication. But you can still do really cool things like polymorphism. So like here, V is a vector of types that implement the shape trait. And so then when I iterate through the vector, I call shape.area on each of the elements, and it knows that this is safe because .area is something that's implemented by the shape trait, which is kind of cool. And one thing that I'm going to point out now, because it's going to be relevant later, is that it's not actually a vector of shape implementers, it's a vector of boxes of shape implementers, meaning that they're all on a heap. And that's because the shapes are different sizes, so a vector of elements of different types, or a vector of elements of different sizes would be problematic. So they have to be in boxes.
Oh, that's a cute name.
Yeah.
So the box does what then?
So the box is a wrapper around the just like putting it on the heap. Instead of calling malloc here, I just call box new, and then that takes care of allocating on the heap, making sure that the allocation didn't fail, and then actually as soon as the box goes out of scope, it frees the memory.
Nice.
So it can operate without a garbage collector.
Perfect.
So I kind of was assuming with the print and exclamation mark, and maybe you're going to get to this, but the exclamation mark, I assumed that it had like some kind of effect. But why would VAC have an effect? I guess like what's up with that?
So the syntax for exclamation marks is exclamation mark means it's a macro.
Okay.
And the reason that print uses a macro is because Rust doesn't support an arbitrary number of arguments, and it uses format strings to print things.
Oh, okay.
Yeah. So and vec also. So forming the vec uses an exclamation mark because it's a macro, because you can form vectors with an arbitrary number of elements. So the macros are needed to kind of deal with that.
Okay. So like see there's like a macro system that you define macros a little bit differently or not?
Yeah, Rust handles them differently. I haven't played with them too much, but I've heard they're kind of cool.
Cool.
They're obviously useful.
Yeah. Vec and println are both very commonly used. So then, I was also going to touch on, I think it's kind of cool, but it's not bad. It's not that unique to Rust, but it has kind of a little bit of support for like a functional style of programming. So like, if I wanted to, this is an example of FizzBuzz using like map and fold instead of just an iterative method. So like, I take a range of things that go from 0 to n, and then for each of them, I replace integer n with FizzBuzz or fizz or buzz or a string, and then I fold that into a blank string by appending it and then appending a new line. A lot, like this is often what idiomatic Rust looks like. Like it's a little funky if you're not used to writing in functional programming languages, but this is often what idiomatic Rust looks like because Rust doesn't have C-style for loops because that would necessitate bounds checking at every iteration, right? So if it were to like instead create a vector of like n elements and then access them one at a time, then it would have to make sure that whatever element it's accessing exists before it checks it, which would incur runtime costs.
Yeah, that's the worst.
So instead, using an iterator, it doesn't have to do that. And also, mapping and some other iterator stuff are lazily evaluated, which is kind of nice. So if the result isn't actually being used, then it's not actually computed. So that, you know, conserves a little bit of overhead.
So what does fold do?
What does fold do?
Yeah.
You give fold 2 arguments.
Okay.
It has a starting value and then it has a closure. So the starting value is an empty string. The closure is the accumulator, which matches, it starts out matching the empty string, and S, which is the recent string that it's iterating through. So it takes an iterator and it has,
Oh, you're just making one big string.
yeah, it's a way of turning an iterator into one value.
Got it.
Yeah.
Yeah. So it's like in Swift we use you like give it an array of stuff and you say like combine, or you say join and separate.
Yeah,
So it's
essentially.
kind of similar to that. In
Yeah.
Ruby you can do this too.
Except that this comes from this comes from functional programming languages. So
Right.
like this is like a list, like this is how you do things. So it's a
Okay.
little bit more flexible. Yeah, it's kind of cool. All right. So now I'm going to talk about the memory model, which is kind of the interesting part, but it's also the part that it's hard to wrap your head around. As far as I'm aware, the only real way to do it is to just read the doc several times and then fight with the compiler for a summer. Okay, so the memory model is how Rust can avoid lots of entire classes of runtime errors. And so before explaining how it works, we're going to try to classify or understand why lots of memory errors happen in C and C++ in non-garbage collected languages. So this is a trivial example. We create a vector, add stuff to it, get a reference to the second or third element, and then we do some random heap shenanigans that is totally safe. It leaks memory, but it's not relevant. And then we add more stuff to the vector, and then we print out the second element again, and maybe something went really, really wrong. Does everyone, or does anyone see what went wrong?
Vector was initially created on the stack.
Yeah. Yeah. So the issue is that vector moved, right? Because as soon as you resize vector, it might have to allocate more space because of our random heap shenanigans. There might not be space left for it to allocate, right after where it would have allocated. So instead, it has to move. So now the pointer is pointing garbage instead of 2. So this arises because V here is both something we can reference and something that we can change. It happens because of the vector, because our memory is both aliasable and mutable in the same scope. So Rust, by limiting that compile time, by making sure that a variable is only aliasable or XOR mutable, then Rust can check at compile time whether these kinds of errors will happen. So that's just an overview of how it works.
It's pretty awesome.
Yeah.
Nice code. That's how I prefer to write all my code.
So if we try, so the rules of ownership, so ownership is the first part of it. And the rule is that, so Rust doesn't let you do raw pointer arithmetic or whatever.
I love it. I hate that.
So that means if you, for is new, the only way to reference that, you can't reference that by its address, you have to reference it by A, the binding that is pointing to it. So the Rust system of ownership says that A now owns the memory of this location. And if we, and so we can, you know, we can okay, and so we can do random things with it that, you know, make sense that they should be able to work. However, if we try to do something like this, we try to set B equal to A and then print A, then we're going to get a compile time error because A has been moved. Because as soon as we set B equal to A, B took ownership of A's value. So A no longer owns it, so A can no longer reference it. Similarly,
So you're never gonna alias.
yeah. Sorry, I'm gonna plug in that's needs to be updated. So if we do something similar with a function, so if we try to print a value, and this function takes x, which is of type box int, or box, you know, signed 32-bit int, then, you know, then we're not going to run into any problems. But if we call print on A, and then we try to set B equal to A, we're going to have a bad time. Because print consumed A. It took the value x, and it didn't return anything. So A's ownership was transferred into print, and then as soon as we go out of scope here, it was destroyed. So A no longer exists here. So that is kind of inconvenient. So we could do something like